Hello students, good morning. In last lecture, we have discussed about the Einstein's postulates of quantization of energy, which are from the photoelectric effect. Now in this lecture, we will discuss about the De-Broglie hypothesis, or this De-Broglie also called as the De-Broglie. So here De-Broglie proposed a theory in 1924 on the basis of symmetry existence in nature, that the radiation have a dual nature. That is, we can say that this radiation sometimes act or behaves as a wave as well as behaves as a particle. We know that matter consists of particles, and sometimes these particles also shows the wave-like properties. These particles also shows the wave-like property. Wave-like property. So here in this point, the De-Broglie used the properties frequency nu, the wavelength lambda of the wave, and proposed a relation to connect this with the particle properties. We know that the energy E and the momentum P or energy of photon is given by E is equal to h nu, where h is the Planck constant, E and u is the frequency of photon. If P is the momentum and E is the energy, then the relation, we can say this is P is the momentum, then P is equal to E upon C, where E is the energy of photon and C is the velocity of photon, and then P is the momentum. Momentum of photon. Therefore, P is equal to E upon C. This relation is valid for massless particle. Here relation massless particle. Photons are the massless particles. Therefore, this relation valid for the massless particle traveling with a speed, that is c, or speed of light. C is the speed of light. We know that the Einstein's equation, according to Einstein's equation, what is the Einstein's equation? That is E is equal to h nu. That energy associated by the photon is equal to h nu, where h is the Planck constant and nu is the frequency. Then put this value in this equation. We can call the equation 1. Therefore, P is equal to this E upon C is equal to h nu upon C. But we know C is equal to nu lambda. That is velocity of light, the relation between velocity, frequency and wavelength. We know the relation between velocity, frequency and wavelength. That is v is equal to n lambda. Then also this equation can be written as this type for the wave velocity, that is c is equal to nu lambda, where c is the velocity of light, then nu is the frequency of light and lambda is the wavelength of light. And from this we can say the 1 upon lambda is equal to nu upon c. Put this value nu upon c is equal to 1 upon lambda in this equation, then we can write the h upon lambda. Therefore this p is the momentum, p is equal to h upon lambda. So De-Broglies proposed that the moving particle of total energy E, this is the relation for the moving particle of total energy E and momentum P has associated with it, and this is a relation analogous to the photon. He suggested that wave and particle properties of matter can also be described by the relation, by this relation. Thus, the frequency and wavelength of wave associated with the material particle of mass m moving with velocity v are given by the frequency and wavelength of a particle of mass m moving with velocity v can be given by, we know that E is equal to h nu, therefore nu is equal to E upon h. The frequency of particle is equal to E upon h, as well as for the wavelength from equation 2, that is we know that the equation P is equal to, we have derived here, the equation P is equal to h upon lambda, equation number 2, and therefore from this equation lambda is equal to h upon P, that is wavelength is equal to h upon momentum. We know that the momentum of particle of mass m moving with velocity v is given by the momentum is equal to mass into velocity. Therefore we can write here m into v, since we know that the momentum is equal to mass into velocity. The momentum of particle of mass m moving with velocity v can be given by P is equal to m into v, put the value of momentum here, therefore lambda is equal to h upon mv. Then De-Broglie referred to these waves associated with material particle as a matter waves. The wavelength of matter waves can be given by this equation h upon mv. Lambda is equal to h upon mv. And this equation is known as the De-Broglie's equation. This equation is known as De-Broglie's equation or De-Broglie's equation. equation or De-Broglie's relation. Now, for a particle of mass m moving with velocity v, then the kinetic energy of the particle, we know that the formula of kinetic energy E is equal to 1/2 mv square, where m is the mass of particle and v is the velocity of particle. Now, from this we can write the v square is equal to this. V square is equal to, take 2 on this side, then we get Ek or E energy into 2 divided by this m. Therefore V is equal to under root of 2 E K for kinetic energy. Therefore we can write here upon m. Then put the value of v in this equation, say equation number 3 in De-Broglie's equation. Then we will get the lambda is equal to h upon m. V is equal to under root of 2e upon m. Then we can write here h upon m. We can take under root of m above. Therefore we get this m upon 2e. Okay. If we take this m inside the square root, then we will get m square 2e k. This m square will be cancelled m, and therefore this will be equal to h upon under root of 2m e k. That is, wavelength is equal to lambda is equal to h upon under root 2m e. This is the wavelength of the particle of mass m and moving with the velocity v, and the energy associated by this particle is E, kinetic energy E. If this is the equation of particle of matter, then if a particle is charged particle, for charged particle we know that a charged particle of charge q, charge on the particle is q, and accelerated for rest through a potential difference v. Due to this potential difference, a charged particle q will be accelerated. Then the work done is equal to, the work done is q into v. This work done, we know the formula of work done, we have discussed in 11th class, and therefore work done is equal to q into v. And this work done is nothing but the kinetic energy of charged particle, is equal to q into v. Therefore kinetic energy of charged particle is equal to q into v, and therefore this can write E k is equal to q into v. therefore we can put this value in this equation for this lambda is equal to, this is the value of equation of lambda, therefore lambda is equal to h under root of h upon under root of 2m, put the value of E here is equal to Q into V. Therefore, the wavelength of charged particle by the De-Broglie, we can write wavelength lambda is equal to h upon under root 2m Q into V. This relation holds for any charged particle. For example, this holds for electron or proton, or for even charged ions of mass m. Then if the V is very large, in this case V is large, that is in kilovolt, also in this case this relation is valid for a large value of potential difference. Then for electron moving through a potential difference V, now if an electron moving through potential difference V, then the wavelength of this particle can be given by the h lambda is equal to h upon under root of 2m, where q is the charge of the particle, and we know that the electron carries a charge of E into V, where E is the charge on electron, h is the Planck constant, m is the mass of electron, and V is the potential difference. In this case, here potential difference only a quantity which is variable, but other quantities are constant. Therefore, h, 2, m and E, these quantities are constant. Therefore, we can put these values of these quantities in this equation. Then we get h is equal to 6.626 into 10 raised to minus 34. Then h is in joule second. I am not writing the unit of these all quantities. Here 2 into mass of electron. What is the mass of electron? 9.11 into 10 raised to minus 31 kg. And then the charge on electron. Here E is the charge on electron. You know the charge on electron is 1.6 into 10 raised to minus 19 coulomb. And V is the potential difference which we apply. The V is variable, therefore we cannot put the value of V in this equation. We don't know about it, therefore V will be as it is. If we calculate this, then we get the value or calculation 1.228 into 10 raised to minus 9 If we take a multiplication and division of these all quantities, then this will be equal to 1.228 into 10 raised to minus 9 divided by this V. This V is the applied potential and which is in the volt. In volt. This V is in volt. And this is the value of lambda in meter. This is in meter. But when we take this 10 raised to minus 9 on the left side, then we get the lambda in nanometer. Then lambda in nanometer is equal to 1.228 into 1.228 upon V. Lambda in nanometer. Or we can say this is the value of lambda in nanometer. 10 raised to minus 9 is equal to nanometer. And therefore 1.228 upon under root of V. 10 raised to 9 is equal to nano. Minus 9 is equal to nano. Therefore, when we take the lambda in nanometer, this will be equal to 1.228 upon under root of V. Okay, thank you.